now we have got a flux profile, that is QR equal to SCR by 2 plus C1 by R. Now to eliminate C1, we require boundary condition. Here in our question, we have single phase. For single phase, we require at least two boundary conditions. Right. We will be seeing each and every boundary condition which we specified earlier, and we will be seeing whether they are applicable or not. So our first boundary condition was the temperature may be specified at the surface. That is, let's say at distance r, your temperature will be T naught. This boundary condition is applicable over here. Coming to the second boundary condition, that is, the heat flux normal to the surface may be given. This is not applicable over here. Our third boundary condition is at interface the continuity of temperature and kind of heat flux normal to the interface are required. This boundary condition is not applicable over here. Why? Because we do not have any interface. We just have a solid wire and there is no fluid flowing outside there and there is no interface. That is why the third boundary condition is not applicable over here. Fourth boundary condition was at solid fluid interface, the normal heat flux component may be related to the difference between the solid surface temperature T naught and the bulk fluid temperature TB. Again, this is also not applicable to our case. So far only one boundary condition is applicable, that is temperature at the boundary should be specified. But we require two boundary conditions. So what will be the second boundary condition? Now do you remember we mentioned one more boundary conditions while explaining the boundary condition, and that was logical boundary condition. Here the second boundary condition that will be applicable will be logical boundary condition. What is logical boundary condition? Logical boundary condition says at any r, your flux, that is Q1, that can never be notified, right? So going back to our equation of flux, that is QR equal to SCR by 2 plus C1 by R. Here, if we put R equal to 0, you can see that a flux is becoming not defined, which means C1 has to be 0, so that to make a flux of finite quantity. So our equation will be resolved to QR equal to SCR by 2. This will be our final flux equation. Now, we have got a flux equation. In the question, what we were asked for the flux equation, flux flow profile, and temperature profile. From this flux profile, we need to derive temperature profile now. To get temperature, what do you think? What we have to do? We need to apply Fourier's law of heat conduction. From there, we will be deriving our temperature profile. What is Fourier's law of heat conduction is? It says our flux, that is QR, is equal to minus K dt by dr. We will be equating this equation to our above equation, and it will become QR equal to minus K dt by dr, that will be equal to SCR by 2. Now we will be solving this equation. We will be arranging some terms here and there. We will be integrating it. to get our final temperature profile. So after rearranging, what we will get is dt by dr equal to dt equal to SCR by 2 divided by k into dr. Now on integrating this term, we will get a temperature profile that will be T equal to minus SCR square by 4k plus C2. C2 is our another constant. Now to get exact temperature profile, we need to eliminate C2. For eliminating C2, we will again have to go back to our boundary conditions. So we have seen only first boundary condition that was applicable to our question was the temperature may be specified at the surface. We will be using this boundary condition to eliminate C2. As per this boundary condition, at R equal to capital R, our temperature T will equal to T naught. We will substitute this value to the above equation to finally get the value of C2. From here, our C2 value will come out to be SCR square by 4k plus T naught. Now we'll substitute this C2 to our above equation and we'll get our final temperature profile equation. So our final temperature profile equation will come out to be SCR square by 4k plus SC capital R square by 4k plus T naught. We'll take T naught to the left hand side and we'll take SCR square by 4k common. So after substituting and rearranging the equation, what we'll get is T minus T naught equal to SE capital R square by 4k in bracket 1 minus small r by capital R to the whole square. Now you might be wondering that why we have taken SCR square by 4k as common. Why not any other term? We have taken this common like this because we want R by R to be like this. Because in this case, our boundary condition application will be easy. So now we have got a temperature profile. Now we will be looking at some other terminologies like maximum temperature rise, average temperature rise. All this equation we will be looking at. So
Okay, so now we have got two equations. That is the two profiles that we were asked in the question. That is the temperature profile that we got from here. This is the temperature profile. So this is T minus T naught equals to SE capital R square by 4k to 1 minus small r by capital R the whole square. And the flux profile we got as QR equals to SER by 2. Okay, so now we've got both the profiles. Now we'll be okay. So yes. Now we can calculate the maximum temperature rise from this. So how will we get this? So maximum temperature rise, we know that R is equal to 0. At R equal to 0, we get a maximum temperature rise. That will be equals to T max minus T naught equals to SE R square by 4K 1 minus 0 by R, which will equals to 0. So T max equals T naught plus SE R square by 4K. So maximum temperature we have got from this. Now the next one which we'll be doing is average temperature rise. Average temperature rise. Okay. So average temperature rise, how will we get this? So average temperature rise, basically we uh, we have maybe have learned previously. We integrate कैसे करते हैं रे? Okay, so average, how we calculate? So we've got something like 0 to 2 pi, 0 to r, t of r minus t naught into r dr d theta by 0 to 2 pi integral 0 to r dr d theta. Now you'll be wondering, what is this? So basically, this is for the differential part. Differential part, temperature rise in the differential part. We'll be multiplying this by the total area and then dividing it by the total area. So we'll get the average temperature basically. This is the main basic thing is happening is temperature rise, total temperature rise divided by the total area. So we'll get the average temperature. Now, why the limits? So limits will explain. We have to calculate from 0 to r. So the limits of dr will be 0 to r and the limits of theta. So what is theta? Theta we have discussed earlier this. Theta was this. So this we have to take the complete. So 0 to 2 pi. Okay. So by this we'll get the average temperature. So how we get this? So T minus T naught equals to 0 to 1 second. Okay, so calculating this, so for the numerator, we'll basically do it individually. So numerator, what is the numerator? So numerator is we have got 0 to 2 pi, 0 to r, t r minus t naught, r dr d theta. So tr minus t naught, we know the relation. So 0 to 2 pi, 0 to r. What is t naught? Tr minus t naught. So tr minus t naught is s e r square by 4k into 1 minus r by capital R whole square into r into dr d theta. So this is it. Now it's easy. So 0 to 2 pi, 0 to r, se by se r square by 4k, we can take it outside because it's a constant. R minus r cube by r square into dr d theta. So now doing the integration, it will be se r square by 4k integral 0 to 2 pi of now this. So this will be r square by 2 minus r to the power 4 by 4 r square. Limits will be from 0 to r into d theta. Okay, so this will be equal to, okay, so this will be SE r square by 4k. This will be r square by 2 minus r to the power 4 by 4r square. You get cancelled into the integration of theta will be just simply 2 pi minus 0. Okay, no? So equals to SE r square by 4k into this is r square by 2 minus r square by 4. So this will basically be r square by 2. So r square by 4 now into 2 pi. Okay, so now we'll be integrating the denominator. So what's the denominator? Denominator is integral 0 to 2 pi integral 0 to r dr d theta. Okay, so this is 0 to 2 pi r square by 2 0 to r d theta equals to r square by 2 into simply 2 pi. It's a denominator. Now dividing both these terms, we'll get the RHS, that is SE r square by 4k into r square by 4 into 2 pi divided by r square by 2 to 2 pi. What will you get? 2 pi gets cancelled, r square gets cancelled, 2 and 4 gets cancelled. Sorry, 2 and 4 gets cancelled, 2. Okay. So this is SE r square by 8k. So now we got the average temperature, that is average temperature minus P naught equals SE r square by 8k. By this, we also got the average temperature. Okay, so now we are done with the temperature. Now we can also calculate heat output of the surface. Now, how will we calculate heat output of the surface? So we know the flux profile. Flux profile, we know. What is the flux profile? Flux profile is QR is SE R by 2. Okay, so we have to calculate heat outflow at the surface. Now, how can I calculate the heat outflow? What is heat? So basically, we know heat flux. Now, heat flux multiplied by area is heat. So heat outflow, um, heat is coming in. So basically, the shell was like this. So heat was coming in at R and going out at R plus delta R. So basically, we have to just subtract these two. So heat at R is equals to R is 2 pi RL. So this is the area into multiplied by QR at R equals R. And heat,
Was
okay, so now we know QR at R equals to what? QR at R equals R is SE R by 2. So substituting this and this, so heat outflow Q at R equals R is 2 pi R, sorry, so this R also needs to be capital R L into SE R by 2. Okay, so now just simplifying it to 2 pi nonsense, so it will change to pi R square L into SE. So this is the Also, this is a heat outflow at the surface. Yes, so far we have laid down the theoretical aspects. Now let us look at how these principles play out in the real world problems.
Absolutely. One of the most prominent example is in electronic devices, especially in CPU and GPU thermal management. The tiny circuits within the process generate lot of heat energy, and engineers use these concepts like heat flux, material conductivity to design heat sinks and thermal interface materials.
Yes, now another classic case you can take is the design of nuclear reactors. What mainly happens in nuclear reactor? Here, heat is generated from nuclear fission, and transport phenomena plays a crucial role in removing the heat safely. They rely heavily on the accurate modeling of heat conduction through the reactor core and the coolant systems.
Hmm. And speaking of cooling, in the automotive industry, heat transfer analysis is essential for designing radiators, engine blocks, and brake systems. These components often operate under high temperatures and require precise thermal regulation and prevent failures.
On the other side of the temperature spectrum, let's consider cryogenics. In spacecraft and satellite systems, engineers have to manage extremely low temperatures. Now, here, what helps? Fourier's law. Fourier's law helps determine how insulation and heating elements should be designed to keep components within operational limits.
And let's not forget energy systems, especially solar panels and battery systems. For solar thermal systems, capturing and storing that involves optimizing conductive material. Similarly, in lithium ion batteries, improper thermal management can lead to reduced efficiency or even dangerous failures like thermal runaways.
Exactly, that's where modeling tools come in. Simulation softwares like COMSOL Multiphysics or MATLAB, like we have studied in the previous semester, rely heavily on the heat conduction equations, as we just discussed. Engineers simulate heat transfer in complex geometries to optimize designs before even making a prototype.
This shows that what we study in transport phenomena is just not academics. It's the backbone of engineering problem solving in a wide range of industries.
Exactly, whether it's consumer electronics, aerospace, automotive, or energy, these fundamental principles are the core of innovation.
Wow, Apur, that was quite a journey. From understanding the basics of transport phenomena, diving deep into the Ford's law, and applying it through the Shell energy balance method, it's amazing how everything connects so seamlessly.
Absolutely, and I think what really stood out is how crucial the framework was. Uh, how the crucial the framework is, not was, not just theoretically, but in real practical engineering problems. Whether we're looking at electronic devices, nuclear reactor, or battery systems, the principle of conductive heat transfer are everywhere.
And that's the beauty of transport phenomena. It helps us explain and quantify how momentum, energy, and mass move through systems. Today, we focused on energy in the form of heat, but these concepts extend even much further.
Yes, and understanding the shell energy balance allows us to construct differential equations that describe the temperature profile in a material. It's like peeking under the hood of a system and seeing how everything works at a microscopic level, especially in cases involving internal heat generation.
Also, let's not forget about how boundary conditions play a vital role. Without them, we won't be able to solve these equations or apply them to actual design. Whether it's a fixed temperature, insulation, or convective surface, they complete the picture.
Now, before we wrap up, let's leave our listeners a key takeaway of basically what we did. So, transport phenomena and specifically heat transfer are not isolated concepts. They are part of the bigger engineering story. Mastering them empowers you to design safer and more efficient and more sustainable systems.
Well said. And for our fellow students, let's keep exploring, dig into the map, understand the physics, and most importantly, look at how these ideas are applied in the real world. That's where the real magic of engineering life lies.
So, finally, thanks for tuning into. our podcast. Basically, the topic was heat, energy, and everything in between. Like we started with it. We hope this episode gave you clarity, curiosity, and deeper appreciation of transport phenomena.
Until next time, keep questioning, keep learning, and stay curious.
Bye.